Is that working?
I see a black screen.
Okay.
With your mouse pointed on.
I see. I'm going to switch back to Firefox because I did try switching to Chrome for that, but I don't know if that's gonna. It worked on Firefox last time, so.
Okay, I see your audio going through, which is
Okay.
the biggest point. You just have to put it on the screen.
Yeah. All right. Let's.
I want to share your screen.
Yes. Okay.
Yeah, there are.
All right. Is that
Perfect.
awesome? All right. Hi, everybody. Just some preliminary things. So on the ICFP page, for those of you who don't know, this is a interactive coding experience tutorial on software foundations. And so on the actual ICFP page, you can find a link to this site where it'll have everything you kind of need to get ready. We have the actual textbook, the source code to kind of follow along with, and we have a little cheat sheet of useful tactics that we're probably going to have come up a couple of times, and a short description of what they're doing. All of these are things that we're kind of adding in, so we'll get to see some of these be built up, and it's nice just to have maybe on the side a little reminder. So we're going to probably have to take some time because make sure everybody who needs to be set up with their Cox software and ID of choice is ready. The other option is you can also just be a part of the audience and kind of shout out, because it's going to be interactive where I'm going to be asking questions and we're going to try to collaborate and solve these problems together. All right, so let's just take maybe a couple of minutes. Are people still setting up the software and getting everything ready? Still setting up? Okay, so yeah, let's take a couple of minutes. It's inevitable whenever you do a software foundation style tutorial that it does take some time. There's no way around it. If you have any trouble, raise your hand. I can come over and help, maybe. We'll see. All right, does anybody still need more time to get ready, or are we about ready to start, everyone? Good? Last chance to say anything? All right, welcome to the ICFP Verified Quantum Computing tutorial. I'm Ben. I'm a graduate student at University of Chicago under the advising of Robert Rand. And this is the second time this tutorial has been given. The first was at Popple in 2020. This is a slightly updated version. If you were at the one in 2020, it will be very familiar. Not enough has changed for it to really be a new experience. But we're going to go through it. And just as far as like the structure of this tutorial, I'm going to go through a file with you guys. We're going to try and collaborate. I want people to be able to kind of shout out if you need to. You don't have to raise your hand. Just if you have the next line and you want to share and collaborate, then please feel free. At the end of the file, we're going to have maybe some exercises within the file, and I'm going to have you guys take 5-10 minutes, go over the exercises. You can group up, you can do whatever you'd like, really. If you don't have a computer, it might be a pertinent idea to group with someone who does for that part, or you can just sit back and relax. There's no requirements. So, right, the goal of VQC is to show us how we can talk about quantum computations in a verified manner. So we need a couple of things to do that as sort of background. We're going to have to take a look at how do we actually build the real numbers inside of Coq.
Could you maybe make the font slightly bigger?
Yes. Here, let me just... Is that better? Okay, yeah, and if anybody else is having trouble seeing, please do speak up. Right, so inside of Coq, the real numbers are an entirely axiomatized system. right? There's no sort of way to represent them nicely as on a computer, so we have to axiomatize it and then work around the extraction issues later. We're going to kind of go through how they do it, right? So within Coq, first you just declare your set and then say, okay, well, we'll give it some scope for nice notations and things. And the important things you need when you're defining the real numbers is we want to give it the power of a field. Fields will allow us to use some very powerful automation tools, because we don't want to actually have to, when we get to a quantum circuit, we don't actually want to have to solve these equations by hand. We want this to be mostly automated. Otherwise, it's going to be a bit of a headache to actually get through. So we'll declare the only really important real numbers, 0 and 1. And then all of the operations we need to kind of take these and transform them and find other real numbers, which is just going to be our plus, multiplication, negation, and division, or inverse, really. We can give these nice notations, so that way when we're actually looking at these equations, we can make sense of them. And then we define minus and div in terms of these other operations, right? So minus is just going to be plus the opposite, and div is going to be multiplied by the inverse. And we give those the same notations that you would expect. But so we don't want to have to write everything as R0, R1, and then plus, add them together however many times we need. We need this to be a much more readable system, and so we have to have a conversion from natural numbers in order to give us a way to actually easily write out every real without having to find it ourselves. And so the normal Coq library does this from Z to R, which is, it's harder to prove things, but it ends up being more useful because things like op are a little nicer behaved. And so what we'll do is we'll say, okay, we want to automatically have these natural numbers come in and turn into real numbers. If you just try to do that immediately with defining I and R, you don't get anything. You're going to say, oh, well, this plus is looking for two real numbers, and these are both natural numbers. There's no way you can do that. But we add a coercion, and the coercion will say, okay, well, if my function is looking for a real, it could also just look for a nat. And now we can type check, and 4 plus 5 will type check as a real number. And for very little work, we've actually gotten the basics of a real number system. And so now we have to actually prove or axiomatize all of the field axioms that we need, right? The basic one is just that 1 and 0 can't be equal. We have to insist on that. There's no way we can prove that. We don't have any facts yet. We're going to have to axiomatize commutativity of plus and dissociativity, as well as some inverse for addition and some zero addition to the left, the identity rules. But now we can prove things, right? So now we have enough that we can start to prove the rest. So how would we get started with this? What is the first tactic we might want to use?
Maybe a simplify.
A simplify. So all that's done for us is it's turned this 0 into an R0. So it hasn't changed really much there for us. Are any other ideas? But thank you for speaking up. Anyone else have any other ideas? First thing we need to do. Commute? Yeah, we can do a rewrite with, well, what's the commutation rule? R plus com. It's unable to find the subterm though. Maybe the simple is messing things up. We can try going back, but not quite. But this is right. We're going to have to do this later, right? If you think through the proof mathematically, well, yeah, of course, I can show this by doing a commutation and then using this rule up here, R plus 0L. But what we really need is we need to have our variable in scope first, right? Otherwise, R plus com doesn't know what it's actually commuting. It needs to know, hey, I'm commuting this R and this 0. And if it has the R in scope, then it can figure it out. And then the next idea is,
We'll use the previous axiom.
Use the previous axiom. So let's just apply it immediately. R plus 0L. All goals completed. We can QED, and we've solved that. All right, so R plus op L, right? It's going to start in a similar way. we're going to have to do introduction. We have to get all of our variables. Can anyone sketch the proof for me quickly?
Pretty much similar to the previous one, except we use the other one, the R plus.
The R plus
If we
op R it is.
this, we pretty much have that.
Yeah. Right. And this is unfortunately the kind of stuff you really do have to do when you're axiomatizing the real numbers. You have very few things that you actually know. So you do have to go in and do these things, right? But as we add more things, we can start to prove more interesting ideas, right? -0 is forced to be 0. And it's simply because, well, we can add a single 0 to the left. And then that's 0 plus -0, which by the previous rule is 0. And then we immediately get, well, -0 is 0. So that's the only rules that are actually required to prove something so simple in the real numbers. Right, and so, yeah, we also get some cancellation laws, which can be particularly useful. All this rule is saying, right, let's do our intros. All this rule is saying is that, if you have R1 plus R2 and R1 plus R3, then you can just cancel it so you can handle these equations with addition piecewise, right? If you know the left side is equal, then you can also handle the right side afterwards. And all this is going to require, we do some introductions, we add a 0, and then we use op to introduce our variables back in, right? So the trick here is really we're using this 0 addition to get something to work with, and then we're taking that 0 and we're turning it into our two different numbers. We can associate and rewrite with our hypothesis to turn the R1 plus R3 into the R1 plus R2. So what that's done is change this R3 here. And now we can reverse the process, right? So we introduced a 0 to get these variables because we needed them for the other equation, and now we need to get rid of them. And the process is in reverse now, right? Where we're going back, we're reassociating, we're negating these two, turn them into a 0, and the 0 goes away. And so now we have a nice cancellation law, which can be useful if you want to handle different sides of the equation at the same time. We also get uniqueness of 0, right, fairly quickly. Introduce all your variables. Do a rewrite in this assumption here. And then we're going to do an e-apply. So an e-apply is an eager version of apply. It's different from applying it. It gives us these holes here with this question mark, right? So it will eventually be filled by something if it matches the pattern. And that pattern is now matched, right, by this h. This h has something plus 0 on one side and the same thing plus R2 on the other side. So we can just apply it, QED. Right, so going through, we have some multiplication rules that we can axiomatize now. It's all going to be the same kind of things, right? We have multiplication has commutativity, associativity. We have some inverse rules, and these actually have preconditions on them, right? So we have to assume that it's non-zero if we want to talk about division canceling, because we can't really talk about this division being well stated if it's 0. So we have to have that precondition. We have left identity for multiplication, and we have a distribution law, which tells us how multiplication interacts with addition. So now we want to prove sort of the opposite side version, right? So we have to prove that R times 0 is itself 0, right? So how would we get started with this? Intros is always if I can know how to type, intros is always a good thing to start with. Does anybody have any ideas what we might want to do?
We have that everything times 1 is the same. Do we have it already?
Yes, I believe we
So
We do, yes.
0 is 1 minus 1.
Right, so we're going to turn the 0 into the 1 minus 1, which is given by this, where is it? It's plus op r. R plus, sorry. And we're going to give that a 1. And then we rewrite to the left to get rid of the 0. Which one? How did it? Okay. I'm just going to hope that goes away and fixes itself because I have forgotten the exact tactic there. Right, but yeah, so the idea is now we're able to use one of our rules we just defined, right? Does anyone know which rule that might be? So scroll up. Further. Well, so what was very clever about this one introduction is that now we have multiplication and addition together, right? And that allows us to immediately use this rule, the distributivity rule. So we can mult plus, right? And now we have r times 1, which is what you said you were looking for earlier, right? So of course we're going to do a rewrite r mult 1 r. Oh, do we not have that?
No, we have left, I think.
Oh, we have left. Oh, thank you. So since we have left, our mult com, and let's rewrite that twice since we have 2. Okay, well that's not going to work. 1L, right. So we do have to handle this though. This, we have an r mult op something, don't we? Right, so the goal would be to try and get this transformed to something where we can cancel it with this r. Does anybody have in mind what we might be using for this?
We want to get it in the form where that right-hand side is minus r.
Yeah, we want it to be minus r times 1 is sort of the idea that we were working towards. But I don't actually think we have a rule that can do that quite yet, do we? So we might have to go back and find a different path. Does anybody have any ideas for what we might want to, how we might want to approach this with the very limited number of axioms that we have? Okay, well, let's start doing some searching then, right? Whenever we run into trouble, it's often useful to think about searching. Let's see what we actually know about multiplication. So we do have something that can relate r and 1. We have something there. Let's try searching for R. Use the other one.
Use the R plus L. Left instead of right.
Use left here instead. Yeah, but the problem here is, right, we've run into this issue where we have this negative, this op sign. And we have no sort of way to actually handle that. Okay, so I think for the sake of time, we should move on, potentially, unless anyone has any fresh ideas.
I googled the question because it's not that much quantum, but it's R times 0 plus 0, and then you distribute that.
R times 0 plus 0, and then you distribute that. Oh. So this is what you're saying, and then distribute this?
Distribute and then you can cancel.
And then you can cancel. And then we'll do, it's R plus cancel L, with R1 being R times 0. Is that correct? That's not correct. Okay.
One step back.
One step down?
One step back.
One step back, okay.
We want to use the 0 is equal to minus 0, or we distribute 0 is equal to minus 0, and then, or then if we have the exact thing for them. So then we
Say that one more time. So we want to distribute.
distribute first.
So distribute like this.
Yeah,
Yes.
then change probably the right 0 to minus 0, because we know there. So we have a
Yes.
and then
R up 0.
just one of them, but we might have the same issue. I'm not sure.
Yeah, the problem.
I think we need the 11 here. Actually.
It
This
does.
is so basic.
This is so basic that I'm.
Yeah.
So I'm saying for the sake of time, we can move past this and all. The point of this isn't to discuss the real numbers with you. This is supposed to go much quicker. So yeah, let's try maybe this next one. All right, so we're going to do our intros. We have that R is non-zero, which has given us access to one of our other axioms that requires it, R inverse L. Right, but we're trying to do R inverse R now. What's the pattern? We've seen this pattern before, so we have some idea maybe of what we need to do. I'm going to throw an idea of rewrite. I know that's getting us very far into the proof. So we have, right, the commuted version of this already, R inverse L. So inverse R times R is 1. And so if we just do a commutation, right, then we can just apply R inverse L. And then that's an assumption. QED, we're done. So this is the real reason that we actually cared about getting to this point, right? Is the automation that rings and fields that Coq has access to. So what we're going to do is we're exporting these so that we can use them higher up. But we want to declare that R is actually what's called a ring theory. And we've proven pretty much all of the necessary things that we need, right? So we hand it the ring theory constructor, which is necessary, and then it lays out every single thing it wants us to prove, right? And it's a ring with respect to plus, right? So we're going to say, okay, well, we have left identity, we have commutation, and then we have associativity, and then we have multiplication. Multiplication is commutativity, and we can also associate in multiplication. Then we have distributivity to tell how these two things relate. We have the fact that our subtraction is actually just our opposite function with addition. We're just throwing in reflexivity here because this can be proved immediately by how we defined addition or subtraction to just be plus the op. But that's important for this to actually work out. And then we have the additive inverse, right? So we can have a right additive inverse. And we've now defined a ring theory. We add the ring to our tactics collection. And what this lets us do is extend it to a field theory. Field theory will require a ring theory beneath it, but we also have to have that 0 is not equal to 1. We have to have similar to how op and sub and plus have to be related. You have to have the same thing for div and inverse. And then you have to actually have a left multiplicative inverse. And so we've defined that, we throw it into our tactics collection, and then we can actually use these, right? So we can hand it small little equations, right? We're saying, okay, well, can you just solve this tactic for me? I mean, and depending on how this is defined, if you were working with like natural numbers where you could actually recurse on these functions, 2 would recurse here and it would turn into x plus x. And then if it was left addition, maybe you would solve it with reflexivity. But that doesn't work here because everything's axiomatized. We have to go through and use every tactic, and we really don't want to. So we can use the ring tactic to solve this. It's only using ring operations. It doesn't have any inverse things, so we can use the ring tactic.
Okay. I have a proof for R mult 0 R now.
You do? Okay, let's go back to this. Is it long?
No, it's only 4 letters.
Oh, that's All right, let's go back to it so we can.
That was sort of a joke. You can copy and paste that below because that wasn't actually necessary for the ring axioms, and now you can prove it in one.
Okay. Yes.
Command.
Yeah. So the solution to the earlier problem was textbook ordering.
Well, that wasn't the intended solution. I'm just saying it's a solution.
It is a solution now, right? Because we didn't need this, we can just go ring.
It needs the symbols. That's the funny thing. But yeah, simple ring.
Symbol ring?
Simple enough.
Oh.
Same as you do the other ones. The 0 has to
Oh, yeah, the 0 has to become the R0. That simple is a bit weird. When you have coercion, sometimes a simple will kind of fix things because the coercion actually hides a function in there and doesn't show it to you. So that's a fun thing whenever you're dealing with coercions. But yeah, so we solved the earlier exercise. And fields work in the same way, right? Where fields typically will come in when you actually have some sort of division involved, right? So if we tried to just do a ring here, it's not going to be able to do this. Rings have no concept of division. So instead we have to use the field tactic. And that leaves us with this x not equal to R0. And these look very similar. In fact, they are the same because that 0 back there. What have I done? Okay, because that 0 back there has an I and R in front of it, so it'll eventually become R0. Right, so now we have the standard ordering by way of axioms that we have to enforce. If we want to do anything sort of interesting, we need to talk about the reals as an ordered object. And all we have is we'll have this less than infix. We're going to have it be defined as a parameter, and then we're going to define everything you might expect. We're going to have greater than, we're going to have less than or equal, we're going to have greater than or equal. And they'll all get their own notations in the way that you might expect. And then we have an axiom that says a total order. The total order is just going to say that everything is comparable in the reals. We're going to have one for asymmetry, right? Which will say that if one thing is less than another, certainly isn't the case that you can flip those around and still have that be true. We're going to have transitivity in our relation. We're going to have some compatibility laws, right? So we're going to say if R1 is less than, there should be a 2 there. Or R, no, that isn't R. If R1 is less than R, then R plus R1 is less than R plus R2. No, there is a 2 there. It's hidden, isn't it? Yes, there's a 2 there, it's hidden. All right, so we're going to have our compatibility lemmas, which just tells us how addition and multiplication work with respect to these orderings. And the final core axiom that we need upper bounds. So completeness is going to say that every set, every collection, which can be given by some formula typically, has a least upper bound in particular. This is useful for defining things like square roots, right? Square root is something that can satisfy an equation. X times x is less than 2. The set of all things that satisfy that equation, the least upper bound of which is root 2. This is a standard practice for defining the reals. Right, and so we'll have the definition of what it means to be a bound, which means it is a least upper bound, or it is an upper bound, not a least upper bound. But to be an upper bound just means that for everything that satisfies a proposition, you're larger than it. To be a bound means there exists some bound, or to be a bounded proposition means there exists an upper bound. And then the least upper bound is the bound which is, of course, least. And completeness just tells us, okay, well, for every bounded proposition, we can actually find every bounded proposition that is a non-empty. We can find a least upper bound. So the proposition has to be satisfied by some object. Right, and so we can actually look into how we would actually use this. We don't really need to, and I think for the sake of time, I might skip over this because we spent a lot of time earlier, and I think it's best if we move on from the reals. It's not the most interesting part. We find, no, this is all pretty much the square root stuff, right? So it's walking through an example of defining a square root of 2 based off some proposition, showing it's bounded and showing that, yes, it has a least upper bound. And that is the thing that we then call square root of 2. Which is something that will be useful to us potentially. Square root 2's come up a lot in quantum computing. So it is something we need to have defined. But that is all we're going to do for the reals. I don't believe there are actually any exercises in this one. So we're just going to move on to complex numbers. So for complex numbers, we want very much the same things as the reals, but we want to do less work to get there. Going through all this stuff with the reals it takes a lot of time, and we want to just build off of Cox inbuilt reals. Yes?
Can't get it to work. It says new library. I think
you'll have to. So in the files, there was a make file included. If you run that, you'll compile every file, and then yeah, because the IDE needs to look for a compiled file. It can't just work with the interactive ones. So that's what this line up here, line 3, from VQC, require export real, is it's looking in the...
I already built real, but let's see if it works.
Okay, yeah.
It works.
Okay.
That's it.
Yeah, so we're going to define our complex numbers. There's kind of 2 options that you have. Both of them really depend on a pair of real numbers. Right, so we'll do the same stuff we did before. We'll declare a scope. We'll say, okay, well, the complex is just going to be 2 reals. And we'll define a coercion. And the type of real number we're going for is the real number or complex numbers of the form a plus ib, where a and b are real numbers. And that's what our pairs are supposed to represent. The first object in the pair is a. It'll be the real part of our number, and the second part will be b, which will be the complex part. It's a fairly natural way to approach real number or complex numbers in Coq. And it actually gives us some very nice tools. So we can go ahead and define our coercion the same way, so that way we don't actually have to write out all of these things based off of plus. We can use the same coercion all the way from nats, which will coerce to reals, and then reals can coerce to complex numbers for us. And so, yeah, we'll have generally useful constants like I, right? If you have 1 for b and 0 for a, it's just I. have some notations for 0 and 1. And then, sorry, plus will be defined component-wise, op component-wise, and we're going to be just reaching back into the underlying representation as a pair and the reals in order to accomplish all of this.
And maybe in the interest of time, we should just do the automation, show the little bit of automation that's going to be useful, and jump forward to matrices.
I think that's a good idea. How much time do we even have?
We should have 45 left in this session.
Yeah, that's a very good idea. Right, so automation. Where are we? Interlude PSATs. So yeah, this is the main form of automation that we're going to be using. Right, we want to prove everything that we had to prove previously based off of those axioms. We don't want to throw in our own axioms. The more axioms you have, the worse of a job you're doing, really. So the first thing we're going to do is we're going to have some sense of, I should first give notations for all of these. Everything else is the same way it was, but we also have a norm, right, which is given by first c squared, second c squared, right, the standard norm. And so that has its own notation as well. Right, so running through, we want to project equality for these complex numbers back down to the reals. So all we say is, okay, well, if the first part of our pair is equal and the second part of our pair is equal as real numbers, we should be able to say that the complex numbers themselves are equal. So we do some simple destructions. We simplify these two hypotheses here to do this computation for first and second. And now we have R is equal to R1, R naught is equal to R2. We can substitute them in, and we're done. Right, so this is the main form of automation that we are going to be using. It relies on something called linear real arithmetic, LRA here. The LRA tactic is quite powerful. There are many equations it cannot solve. There's no way to know really which equations it can or cannot solve. But all we're going to be doing is eagerly applying this projective equality, simplifying it, and then trying to see if it can solve those two individual equations that are given by the left and right hand side of the pair. And so running through this is a much easier job now, because in order to prove all of these statements about C as a field, we're really just able to go through and use LRA in this case, but most cases we actually can just use LCA, right? So for commutivity of plus, well, it's because the real number one can figure it out, right? And we can hand that all down for most of these. And then we get our own field theory. And we'll get a couple of useful lemmas, which are going to be the same lemmas that we saw in the reals, but now they're the complex flavor. Distributivity of plus and molt, involutivity of op, things like this, plus 0 on the right. Right, and so once we have this field, we then want to start to talk about the complex conjugate, right? Whenever you're dealing with complex numbers, it's a very important concept to have. So we just define it very quickly, just negate the second part of the pair, which is the complex part. We give it a notation, caret star there. And then we can start proving facts about it. But again, because it's really just doing these very simple algebraic operations on reals, things like LRA or LCA is able to take care of it because LRA can take care of it. Right, so to prove that for some real number, something with 0 complex part, negating the imaginary part remains there. LCA takes care of it. And LCA will take care of most of these lemmas. All right, so we'll come back to that exercise later. So the path forward, now that we have complex numbers as a field, is we have to start thinking about how can we actually define matrices. And the way that we've decided to do this in quantum lib is dealing with this complex sum, which you can think would be particularly useful if you're taking a sum along a vector. Right, and so all it's going to be is it's a recursive function. So you have some function f, which generates from a natural a complex number. And then you give it the nat, which is going to be the sort of the recursive size of it. And it will sum up everything from n to 1 with 0, or n minus 1 to 0, sorry. right? So we have that, well, the first lemma that we would want to talk about, C sum 0 here, which says that, okay, well, for some complex sum here, if everything less than our n is 0, then the sum from n itself is totally 0. So how might we want to get started with this? Induction. Induction is a great tactic to use when you have a recursive function. Oftentimes it will at least point you in the right direction. So now we have the base case. How will we approach this? Let's look back at our definition for C sum. Right, so f n match n is 0, so it should just return 0, which means we can simplify and reflexivity. So now we're in the inductive case. How should we proceed? First, let's simplify to see what we can get, see if it does any computations for us, and it does because it has a successor on the nat, so the match goes away. And now we've reduced our size, so we're going to be able to use some tools. Does anybody have any ideas? What would be next?
Use your induction hypothesis.
Use your induction hypothesis. All right, so let's rewrite by the induction hypothesis. We now have two goals we need to satisfy. First, we need to satisfy that 0 plus fn is 0.
But why don't we use our other hypothesis?
Yes, we have another hypothesis, h here, right? So that tells us that, in fact, f of x can be made to 0 under certain conditions. So let's rewrite by h. And now we have 0 plus 0 is equal to 0. In the interest of automation, we are going to use LCA. It's a simple linear equation. We don't have to worry about those. Next bullet, n less than or equal to s of n. Also automated, right? LIA is the natural numbers version of LCA. So we're able to automate that away, and we can do that rewrite. Now we need to satisfy this. We have some new things we can introduce. And again, we need to show f of x is equal to 0. So h again. This one, we can do LCA, we can do reflexivity, but now we're here. X is less than Sn. How would we approach this? The theme is going to continue to be automation, right? So LIA will work here, and it takes a couple of steps to see why. But in particular, this x is less than n. And then it can figure out n is less than Sn. But LIA just lets us at least try it. It's the first thing we can try. And then if it doesn't work, maybe we have to go back to the drawing board. Okay, so we're going to have a similar lemma coming up next, right, where we're going to be taking these sums, and previously we were saying, okay, well, we have this precondition that makes everything small enough equal to 0, and then the whole thing should be 0. Now our precondition is everything small enough is equivalent on these two functions f and g, and then our sums of size n should be the same. Does anybody want? How would we start? You can give a general sketch too. You don't have to give me an exact tactic. You can say, what is our goal? What do we want? Are there patterns we've seen before that we can replicate?
It's going to look a lot like this.
It's going to look a lot like it. So let's just go through and see how far that can actually get us, right? well, it certainly works in the base case. And we can go through and do the same rewritings. Rewrite H this time. Everything seems to be working nicely because that looks like what we should get. And here, so we can use a nice tactic here. That is the by tactic. This is in particular very useful when you have these proofs that keep growing. We're rewriting H, but H has a precondition. If the precondition can be satisfied by some simple term or automation, then we can just say, okay, well, I'm going to say it's true by this linear algebra solver that we have already. So that's great. And now the inductive case continues. We did basically the same proof before, and we can just say, okay, we'll introduce it, and then let's try the same stuff again, right? Rewrite H. And we're rewriting H by LIA, and then reflexivity solves it. Right, so the by tactic can be particularly a little bit useful when it comes to these things that keep generating preconditions. Right, and so we'll have a similar proof for plus, where this one is very much fully taking advantage of the automation, right? We do induction, simplify LCA, induction, simplify a rewrite, and LCA. And this automation allows us to prove more complex statements, right? Which, like this one, which says, okay, well, if we have some function that can actually be split inside of the sum into two functions, then it's the same as if we just summed up the two functions individually. It makes sense. It's sort of a distributivity rule. And then we have something similar for left multiplication. You can bring multiplication into or out of a sum, requiring, of course, this function structure being kind of exposed. But we can rewrite things and make things work. But yeah, it's fairly fully automated, right? We're going to be able to simplify and try to ignore these horrible looking equations as much as we can with automation. Actually, this one doesn't use any. Right, so here we have a distributivity that we're doing in order to be able to use this inductive hypothesis here. So we're taking this C and we're bringing it into this plus here. Right, so we have C times C sum plus C times Fn. And then we rewrite by this inductive hypothesis now to actually get what we want. Use reflexivity and QED. And then there's a similar proof that'll come for the right side, right? So you can right multiply, you can left multiply into these sums. It's an extension of distributivity where, it's nothing too fancy. Got a couple of exercises that you guys are going to be doing. But yeah, one thing we haven't worked with yet is square roots. Right, and this can be fairly difficult, and they're fairly common, so we want to have some automation to deal with them. So this is going to let us commute the application of square root and div, or inverse, right? So the inverse of the square root is the square root of the inverse. And we can run through this. There's no real reason to look at the details of this too much because we are running on less time than we would like. Right, and then we can do some proofs showing, oh, well, we can actually square this and it's square. And this is kind of the important automation that we get out of this section is non-zero. This will come up quite often. Non-zero, it will try to satisfy any sort of, statement saying x is not equal to 0 for us automatically. All right, and so we have then a library down here of useful terms that we aren't really going to be able to go through too in depth, but they mostly handle C-sums. So it's sort of this is the extent to the right for C-sums, extent to the left. And so yeah, there are a couple exercises in this file, so we're going to take a break and have people go through those no more than maybe 5-10 minutes. So feel free to work together, collaborate. If you don't have a laptop and you want to work on it, you should find someone. but you don't have to.
With it, you can really help to sort of think if you look, there's actually a module, and those are right here, you can do this throughout, so people will locate for reals. And that's how we have compatibility with our locate our reals, and there's our
Yeah, I'm going to go
anyone needs help,
Is there a
You're taking the R multiplied by 0.
Oh, yeah. No, it's funny because I know the class before it really didn't think on them.
There's nothing in the chat, otherwise I would have added this.
And, yeah. And I think doing that part was this class.
If there is an option and it's pretty problematic. Because
You have it on Internet. You don't know.
Yeah. Legit. Right, it's something you do in like some kind of
First idea is
You can rate your ad.
between 3.
It's often done like where you produce a couple of more laws before
Sorry,
and then it's not easier.
4 to 5.
Yeah, that's quite possible to do. Depending on how works with what you're doing.
Yeah.
and then
You
you
want
want
to do
to
the slides right here, the spirit page, the right direction. Realize how that's all.
So you have your
LCA. Inverse LCA 2. That's mine.
It happens. The whole point of us doing this is that like we're gonna have these matrices, matrix computations, and each of those is gonna create like n by n different equations, and so I don't solve that. I don't have to do that, and that can work just because we're actually working with this library. I did like 24 goals, and I'll throw LCA in. Oh, maybe 2.
So here's the question, do you make it a line?
That's what I'm thinking.
Yeah, that's
Probably.
And simple and LMA.
Yeah.
Those could be very simple.
Yeah, just say LMA is apply LCA, or symbol is apply.
Display goal name.
Yes. It does come up because you can show it, but make sure it's
Yeah.
they're doing exercises, just show them interpretation. Show them, point out their dysfunctions really, and show how we're going to keep it.
This is not necessarily about the exercise, but much of the emphasis is actually show
And it's not doing it. Is the are you going to enter error when you tell it like this is a button? Yeah. Let me see. It's probably this one right here. Yeah. Okay. Unable to locate library deal. Did you do make in the in that directory?
I tried to say
So what was it, let's say, between R?
This isn't actually very hard. It's here, go ahead.
So the ring.
Oh, the magic for doing it. I was just saying, you don't want to make a make file from the copy file.
Right. Oh, yes.
Yeah, but what's this like?
Okay.
So it's not exactly
All these.
Where does copy stop to?
Main file's not there.
Yes, well, how I did it was.
Okay, yeah.
Yeah. So
I mean, yeah, so.
Yeah. We tried to make this quite easy, having everything to copy, but there's always something will break.
Yeah, no.
Especially, I don't love the copy.
Sorry,
Get better.
yeah, because.
Computers are terrible.
just add that
Or.
file to your class, so I can export patterns.
Yeah.
Because it's just, and then mention guys every process.
Yeah, no, it's funny actually, the complex file doesn't actually rely on the real files for it because we secretly encapsulated the old reals in a little box and we're using box reals.
Yeah.
But,
It's a clever trick. Okay, so that's been about 5 minutes. For the sake of time, we're going to move on because
I know you guys aren't here to learn about complex numbers. Well, then you picked a great first tutorial session to go to. All right, so, right, the whole point of us doing this is to then build up matrices, and we're going to go through this one much faster. Right, so the way we actually define matrices in Quantum Lib is based off of functions from naturals to complex numbers. This gives us a sparse representation. Right, and we do all the same stuff, right, where we'll bind some scope. And then we have notations for vectors, right? It's a matrix N1, and then square matrices. And we have some ways to build them very quickly. We have an equivalence that's going to be important that has some preconditions. That's why using things like the bi tactic ends up being very important. The precondition is that, well, they're equal within the balance, right? We have some basic things. I'm going to fly through this because we don't need to spend more time on this stuff. Right, we'll have notations for identities and zeros, and we're not going to do any of these exercises either. But yeah, in particular, it really is just us saying, okay, well, yeah, it's a function from nat to complex, and we define multiplication, we define everything we need. We have trace, we have multiplication, we have Kronecker products, we have an nth degree Kronecker product. Well, that's probably I typed something, yeah. Right, so we have repeated Kronecker products, we have transposes, we have adjoints. We have dot products, we have inner products, outer products, and all this has nice notation, right? So you'll be able to see these in nice equations on the side as you're actually doing your verification. There are some compatibility lemmas, right? So this allows us to do some fancier, some fancy things based off of, well, if these are equivalent on their within their dimensions, then the traces are going to be the same function, right? This allows us to, say, okay, well, we can do rewrites with this. We're actually building up, if you've done anything with relations in Coq and parametric morphisms, that's what we're going for here. We want the ability to rewrite within matrix equations, right? So we don't want to just be dealing with the top level equations. We want to be able to say, okay, there's a smaller part, and we know the smaller part is equivalent to something else. So let's do a rewrite within it. And then all these compat lemmas are really doing is it does the heavy lifting of saying, well, okay, everything outside remains the same. There's quite a few of these, and they all get their own parametric morphisms. And so then we actually get to like the actual processes, the properties, right? We'll have some associativities. We'll have how adjoint distributes over multiplication, involutivity of the adjoint, and how Kronecker and the adjoint interact as well. Right, and so then we get to the automation, which is, again, we really just want to automate everything. As we automate more things, we then can build another layer on top of it. That layer can use the automation from below. So we have some automation, right? The one in particular that's useful here is BiCell. BiCell tries to solve a matrix equation for you by taking a look at what the dimensions of the end result would be, splitting it up into functions, which correspond to the value that should be there after it goes through the matrix computation. And then it will try to then, if you use the more powerful LMA tactic, which is just LCA, but lifted to this context with matrices, it'll split them up into each cell. Each cell gives it an equation, and it tries to run LCA on those equations. Right, and so we can then use this to say, okay, well, 0 scaled against the identity, automatically solve, prove that's 0. Right, and so yeah, then we get a couple of useful properties showing us how identity and Kronecker interact. Right, so the dimensions just end up multiplying, and it's still an identity matrix. Scaling all the normal algebraic things, right? Like, so if you scale by 0, it becomes 0. If you scale by a 1, it stays the same. Multiply by a 0, it becomes a 0. Multiply by an identity, stays the same. All the normal things you would expect to have and would certainly want in a matrix library. And yeah, all the automation we're really going to be using is later on is in LMA. So there is simplification. This is actually a useful tactic as well. So when we're dealing with, like, simple is a great tactic, and Cockme use it all the time to try to do some basic computations for us. msimple is going to try to do some basic rewrites for us. It's going to try to say, okay, well, finding context, anything useful with, like, an identity chronicled on the left side, or particularly this is a 1x1. And then we can just get rid of it. And so if we have a very complex equation, one of the first things we want to throw at it is going to be msimple. Yeah, so that's all we're really going to cover for the matrix library. I know that was lightning fast, but I want us to at least get to qubit, right? Because this is sort of where we're actually, like, what we actually care about. So we've done all this work to be able to describe qubits. And a qubit is just going to be represented by a vector underneath the hood. And we have some nice definitions here handing us a 0 qubit and a 1 qubit if we need to create them. And then we'll have some notations. We have the bracket notation, right? And some simple notations for when we're multiplying these things together. And so we then have the ability to decompose into the spaces, right? And this is sort of going to be very useful for computation, right? Because you can decompose into a basis and then perform computations on the basis states to actually solve your equation. So we do have to prove this, though, right? So we have to prove that we can't actually decompose any qubit. So how would we get started? We're looking at an existential. So I'm just trying E exists. And just delay that for later, right? And now what we've kind of have hidden under here is this matrix equality. And we can actually get rid of that by doing an intros ij, which is going to be our dimensions, hi and hj, which tell us the size of the dimensions. Okay, so we can't automate that away, sadly. Okay, so, right, we're going to have to look into okay, so actually let's step back because I made a mistake with the E exists. That makes it far too complicated. We don't need that. We know what these should be, right? What alpha and beta should be. That is, we know what this decomposition looks like. In particular, we know that alpha should be 5, 0. What's happening?
It's the second 0 because it's a matrix, not a.
Yeah. right? And it should be phi, and beta should be phi of 1. And now we can do this introduction and try to automate it now. LMA, that's worth a shot.
Well, you need to do that before the introduction.
Don't have to.
Oh.
You just do it.
Yes, we can do. Oh, let's see, I should have done the automation. Right, so by knowing what these are already, we then just can use LMA, and it can solve that equation for us. Right, so then we have a definition for what a well-founded qubit is, which is going to be that the norm of the sum of the norms of each of its indices is 1. Which is equivalent to this statement that says that a qubit times its adjoint is, or a qubit is well-founded if and only if it multiplied by its adjoint is 1. We might want to skip that. We have about 20 minutes, Robert.
What?
Do you think should we skip that?
So I think one thing is how many people know quantum and don't know coffee? How many people know coffee and not quantum? How many people know both?
That's a good question.
So how many people actually know sort of basic quantum computing? It's not the entire audience, so I would spend just a little bit of time explaining kind of what all these lemmas, so what qubits are and what these lemmas are actually showing, and then we can breeze through them. But I think it is kind of the point of the book is to explain. So what we just proved was that so qubits are just vectors, so qubit is just vectors with two numbers in it, and sort of our basis qubits are the 0 and 1 qubit, which means that 1 in the first or second position. So we showed that we could decompose any one of those into alpha times 1 basis qubit plus beta times the second basis qubit. That's simple linear algebra. The other restriction on qubits is that their norms. Sorry, I'm stealing your thunder a little bit. Your norms should be equal to 1, and there's a few different useful ways to kind of represent this piece of information. So we've defined well-formedness in terms of projecting out the two elements and saying that they sum 1 there. But another more convenient way in practice might be just to say that we can multiply it by its transpose. Thanks so much. So another way to say that a qubit is well-formed is to say that if we multiplied it by its transpose, or rather its conjugate transpose, where we conjugate the elements, we just get out the 1-by-1 identity matrix. And there's actually a bunch of nice equivalent ways to prove that qubits are well-formed that are equivalent that we might use in practice.
Right. Yeah. So actually going through this from the Coq point of view is, well, we have this if and only if statement. In Coq, you use the split tactic, and then you prove one direction and then the other. And so now we have this well-founded qubit. So we have this assumption, right, that this property holds up here, and we're going to try to go in the other direction. Right, so that means that we actually have to somehow find a way to get to this. Right, so we're going to have to try to find a way to work with that actual adjoint. So does anybody have any ideas how we might want to progress?
Why doesn't the LMA work?
You can try LMA. Unfortunately, it doesn't.
We have to use LMA. Okay, I guess the tactic here would just work, so if it fails, it goes back right on the by side.
Right. Yeah. So we can. So, sorry. Say that one more time.
No, nothing.
Okay.
I was going to ask you what is the first part of LMA and the expert.
Yes. Okay, that's what I thought you were saying, and then I typed it in, and I was like, oh, yeah. So the first part of LMA, LMA isn't working because LMA tries to do this by cell and then LCA, but we weren't actually able to kind of break this down, so we have to do this a bit more manually by using by cell. Could try to simplify and see what it does anything, but it does not progress. So part of what makes this a problem.
Can't you evaluate? Can't you just evaluate on the right hand side and then really evaluate it? Why is it not simplifying?
So it's not simplifying because it can't look past this phi here.
No, the RHS.
Oh, the right side?
Yeah.
I mean,
That's
that is weird. Yeah, that feels like it should be.
Matrices just by default don't unfold because it would be costly, so you just have to say unfold I if you want.
Yeah.
But
So,
then you do get something that looks better.
yeah. But yeah, so on the left-hand side, we can't actually get past anything because we don't know what this qubit phi looks like. But thankfully, we proved something recently that lets us actually look and take an arbitrary qubit and look at what it might look like, right? So we'll rewrite a qubit decomposition, or we'll destruct the qubit decomposition of phi. Right, and so now we have, okay, we can turn this into this thing. Oh, it's not, it doesn't like that. Oh, because it's a strict equality now. Oh. Sorry. So that won't work actually, because we've done this by cell. Are we able to do this earlier? Right, so now we've done this before we did the by cell, and we've turned it into things that we can potentially compute with, and now we will try LMA. Unfortunately, it doesn't work.
I think you unfold by trying to. Does the joint unfold automatically?
I don't know if unfolding adjoint is quite the right path. We can try it though. So you would say unfold adjoint before by cell?
No, wait. Where is it defined? Or is it some inbuilt?
And direct is not the matrix file.
Oh, from the matrix, right?
It's not tractable.
Yeah. So we can. We can at least look up things that relate to the adjoint, see how that would help us. Right, we do have a distribution rule for adjoint with m molt and m plus. So we can do this qubit decomposition and then what was the name of that? It's m plus adjoint. Maybe not try LMA? No, it's not working.
Maybe we should unfold the matrix product. Like I think LMS not working because it's not substituting fully beyond some getting cells on the.
So you think unfold m molt,
Yeah, right.
and then okay, yeah, could be.
Plus, I don't know now.
No, maybe I tried this qubit decomposition thing. I'm not convinced that was the right path anymore. So maybe we'll just try doing these unfolds. and then LMA.
You still need to always substitute the qubit, right?
So,
And then you have to use W to actually scratch. Yeah.
Yeah, it's not.
What else is it?
How about there's a tactic. Qubit. Wait, we don't have qubit simplify yet, do we? There's one of the tactics here on the cheat sheet, but it's further down.
yeah, so there's, what I would be doing is do it by cell, and then there's something proved in the complex B file called conj mult norm q that sort of translates between them. So you can do that by searching adjoint for, sorry, the C norm that is.
C norm 2.
Yes. And see, that's exactly relating the two things there. So we could rewrite that in. We might have to unfold the W of qubit in H, but once we rewrite that, we get something that's very close to the goal.
So unfold the W. Oh, yeah. Right. And then that exposes the C norm.
Yeah.
And then we can rewrite conj mult norm 2 in H. Oh. Did we not need to do the qubit decomposition?
We didn't. I mean, we didn't.
Oh, okay.
We didn't need most of this. Honestly, I wouldn't just move on because
Yeah.
we're running out of time. But that level alone gets you sort of 90% of the way there, and we didn't spend time on it in complex stuff.
Yes.
But
Okay, yeah. So you have these two alternative ways then of talking about whether or not a qubit is well-founded. And it makes it now fairly easy for us to go forward and say, okay, well, we can use LCA to find out that these qubits are in fact well-founded because this is just an equation in the complex numbers. Right, and so then we have our next lemma, valid qubit function, which is just going to be sort of a way of discovering, right, the proper definition that we need to make something respect the well-founded qubit property, right? So we need it. Our operations on our quantum space need to respect the fact that they take qubits to qubits. In order for us to discover that, we create this lemma, right, where we say that, well, there's some property of matrices, 2x2 matrices, that for any two matrix, if that property holds and you have a well-founded qubit, then the result of the computation, the multiplication, is itself well-founded. Right, and so what this ends up doing for us is this will get us to discover the definition that is necessary, which is a unitary matrix. Right. Does anybody know the definition of unitary off the top of their head? It times its adjoint is the identity. The adjoint is its inverse. But yes. Right, so right, so this is as you going through this textbook, this will get you to a point where you have an assertion that you make, and you'll state this property, and be able to actually build up. Oh, well, this unitary property is the one thing that's necessary. And I apologize, I've forgotten that proof. Right, but then we get from this the unitary matrix definition, which is just a square matrix, and then we call them well-founded if they have this property that the matrix times its adjoint is the identity. And then from there, we get the X gate, and we get to show that it's well-founded with some automation, and we can talk about how it operates on each of the basis states. You can build the Y gate and do the same things, the Z, H, but you have to do a bit more effort to show that the Hadamard is in fact well-founded. Right, so we have a lot of automation that we're using here. We're auto-unfolding with some database, which from the cheat sheet is the one that mostly deals with the matrix and quantum expressions, right? So, and then we turn into a bicell, and LCA works for most of these. If we don't have LCA here, we have 4, but thankfully LCA can solve most of these equations for us, the 0 ones in particular. And here we show it's equal by doing a projective equality, which is the property that we're using for LCA to say, well, if we look at each of the individual parts of the pair, one has one equation, the other has the other equation, and we can automatically eliminate one of them, and then we get this horrific thing full of square roots, but we have some nice field automations, field simplify. And then again, we can go and do, it doesn't work there. So we field simplify, handle our square roots, and then can use non-zero to finish off that last part. And then the second part of the lemma goes exactly the same. So then we start to be able to talk about, okay, well, we have our Brockhead notation, we can have plus and minus. And we can talk about how Hadamard operates on the basis states. Right, so we can note, okay, well, Hadamard on plus gives us 0, Hadamard on minus gives us 1. And we can show, okay, well, Hadamard twice is going to be a self-inverse, or it's going to give us back the original qubit, right? And so, does anybody have a short idea on how we might want to approach this? Because this is for arbitrary qubits.
Apply the initial lemma twice.
Which initial lemma?
The definition of H.
The definition of H. The problem is we can't compute anything because we don't know what phi looks like, right? But when we're working with linear algebra things, sometimes it's easier to operate on the basis rather than on some arbitrary vectors. So we can do a qubit decomposition. That one should be working.
Is it the other direction?
Maybe.
Does it exist, still exists, and then an equation?
Oh yes, thank you. It's an existential, so we actually have to do a destruction, and then that gives us the equation. Then we can rewrite with H2. Thank you. Right, and so. At this point, right, we want to have this multiplication distribute over the addition of these two states. Because I don't think LCA will do it for us now. Or we could just do it by cell, which I think is okay. Well, we are out of time, so thank you guys for coming. I will let you leave now. There is another section continuing where hopefully we will jump into the squire.v file, which covers the Squire language and how we actually use these semantics in order to prove things about Squire, and have built some automation up in there.
I have a question.
Yes.
Are you interested in well-founded qubits?
We're interested in well-founded qubits. It's sort of it's a property that we put on top of them because a qubit, Actually, no, because you can have scalars, can't you?
What's the question?
Why are we interested in well-founded qubits?
Because,
I mean, it's not necessary, as I understand it, right? It's nice to have.
it's a property of qubits that there's the sum of the squares should be equal to 1. If you try, you could potentially, say, oh, any vector is a qubit, provided it's non-zero, and then we could somehow rescale it to 1, and then you would get a lot of equalities that you don't like.
Yeah.
Like, 2, 0 being equal to 1, 0. You already have certain things that are equivalent, if not identical, like negative. A qubit is on its own equal to that qubit. But I don't think you would want that. You wouldn't want more issues like that.
Yeah.
And well-founded is the terminology, or well-formed?
Well-founded?
Yeah.
Yeah. The words sound very similar. Is well-formed something that's used somewhere, or?
For me, it would be a well-formed condition or something.
Okay.
I think it's more than well-founded. Sounds like it's talking about, valid sets that are, that won't bump into Russell's paradox or such. And I mean, I guess there are other uses of well-founded. But yeah, here. I intended well-formed when I wrote it. Or, I think that's the only reasonable estimate.
Okay, well-formed then. My mistake.
Should be the subtype. Factor 2 should not be the factor 2.
Ideally, well, that's a